Hello everyone, and welcome to the Central Force Post Lab based on a simulation you've hopefully been working with. So first thing we need to do is to go through the three different parts of the lab, and so that would be basically finding the relationships and building the math models, and then at the end I will shove all three math models together into one big math model to govern them all. So first third of the lab, you varied the mass of the object, and you let the simulation measure the force in newtons, mass in kilograms. And when you graphed your results, you should have gotten a nice linear graph going through 0, 0. And since the graph is linear and contains 0, 0, that of course means that the force and the mass are proportional. So if the object had twice as much mass, it would have, or would require, twice as much force to keep it moving in a circle at the same speed and same radius. If it only had half of the mass, it would only require half as much force. So to build the y equals mx plus b math model, the y variable, what we graphed on the vertical axis, is of course the force, and that equals the slope of the graph, which using the simulation should work out to be about 3.3. Now let's talk units here. We could just do rise over run units, but I want to simplify these because it'll help us understand later on what's going on. So units-wise, we have units of rise, newtons, units of run, kilograms. Well, that doesn't look like it reduces, but remember, a newton, the unit of force, comes from Newton's second law, which is net force is mass times acceleration. 1 newton, if you remember, is the force required to make a 1 kilogram object accelerate at 1 meter per second squared. So a newton is a derived unit. It's a name we give to a kilogram meter per second squared. We plug that in, notice that the kilograms cancel, and we're left with units of meters per second squared. So I'm going to throw those in on my slope over here, the reduced units. Now, those units I hope look familiar to you. Right? Those are units of acceleration. So it looks like the slope of this graph has something to do with the acceleration. The x variable is the mass. The y-intercept should be 0, which means if there's no mass, there's no force. Kind of makes sense. If there's no mass, there's no object, so you don't need a force. And that means that this is the end result here of our first third of our lab. And notice, really, it's just forces, mass times, and acceleration. It's really just a version of Newton's second law being applied to the situation of an object moving in a circle at a constant speed. Now, in this third of the lab where you varied the mass, you kept the radius constant at 30 meters and the speed constant at 20 meters per second. So first third of the lab. Right? Second third of the lab, you varied the speed of the object that was moving in a circle, speed in meters per second, and measured the resulting force needed to keep it moving that way in newtons. This one did not end up being linear right away. It ended up being our old friend, the top opening parabola. Right? We've seen that in other cases, and hopefully you remember that to linearize this, we need to square the x value, in this case the speed. So if you graph force in newtons versus speed squared, and notice you have to square the units as well, so meters per second becomes meters squared per second squared, that gives you a linear graph that goes through 0, 0. So force is not proportional to speed. Force is proportional to speed squared. It's a little more complex here. And that means, as you see on your lab sheet, that if you double the speed, if you want the object to go twice as fast, you don't have to pull, or you can't pull twice as hard. You have to pull 2 squared, or 4 times the force to get it to go twice the speed. And if you triple the speed, if you want it to go 3 times as fast, you have to go or pull with 3 squared or 9 times the force. Right? The force increases faster than the speed. That's why the graph gets steeper and steeper up here originally. So let's make a math model out of this linear graph right here, right? Out of the linearized one, y equals mx plus b, of course. The y variable is the force. And that equals your slope, which in this case works out to be about a third, 0.333. Units, well, let's go through the units and reduce them again. We have units of rise of newtons, units of run of meters squared per second squared. But remember, a newton is a kilogram meter per second squared. That means one of the meters cancels, and both of the second squareds cancel, leaving us with units of kilograms per meter. Kilograms per meter. So it appears that this slope has to do with the mass, right, of the object, and meters is a unit of length, so maybe that's the radius. Right? Looks like this slope has something to do with the mass and the radius. The x variable is not speed, that's not linear, it's speed squared. The y-intercept is still 0, which means that if it's not moving, you don't need to put any force on it, right? Things will stay at rest all by themselves without a net force, Newton's first law. In this third of the lab where you varied the speed, you kept the mass constant at 10 kilograms and the radius constant at 30 meters. As long as you did that, the simulation should have pretty much given you this exact slope. So that's the second third of our lab. The last third, which is the part that's really hard to do in a laboratory, is to vary the radius, right? The radius of the circle that it's moving in. Now this one gave you the most exotic looking graph, right? Wasn't linear, wasn't a top opening parabola. It was this. Right? If you remember, this is called a hyperbola. What does it mean? Well, look at the graph. As the radius gets bigger, what happened to the amount of force that was required? It gets smaller. Right? As the radius gets bigger, the force gets smaller. What kind of a relationship is that? We've seen it, not very often, but we have seen it. When one variable gets big, the other gets small. It's called an inverse relationship. And so to linearize this one, you should have inverted the radius. Right? So we do 1 over the radius in 1 over meters. I got to invert the units too. That gave you a linear graph. A linear graph with a 0 y-intercept, which means, no, force is not proportional to radius. Force is proportional to 1 over the radius. Or, you could use the magic word, and you could say force is inversely proportional to radius. Don't use both. Don't say inversely and 1 over. It's like a double negative, right? So it's either proportional to 1 over the radius, or it's inversely proportional to radius. So let's think about what that means again, because we haven't seen this very often. On the lab sheet, I said, well, what if you had twice the radius of a circle that it was moving in? Right? So if you double the radius, keeping everything else the same, right? It's not double the force, it's 1 over that. It's half as much force. See, we get that? We flip it, right? We invert it. And then the next question was, what if there's only 1/3 of the radius? That means we made the radius smaller. Look at the original graph. If we make the radius smaller, the force should get bigger. By how many times? Well, it's an inverse relationship. The inverse of 1/3 is 3. Right? So if we cut the radius down to 1/3, we should get 3 times, or require 3 times the force to keep it doing the same thing. A little tricky one there. And if you're thinking, boy, those kinds of questions would make a good concept builder, oh, they do. Believe me. We'll get to those in the next few days. So we're going to make a math model of the linearized graph over here, right? Not this one. That's not linear, but this one, y equals mx plus b. The y variable is, again, force. The slope you should get is about 4,000. It's a large slope. Units, well, let's check those out again. Units of rise, newtons. Units of run, 1 over meters. But a newton is a kilogram meter per second squared. Well, that doesn't like cancel out quite, but remember what that line means right here. This horizontal line means divide. So if dividing by 1 over a meter is the same as multiplying by a meter, so that's a kilogram meter squared per second squared, right? So this is dividing by 1 over a meter, which is the same as multiplying by a meter. So it's a kilogram meter squared per second squared. Now you might be saying, well, how does that help us? Well, look at these units. Kilograms are units of mass. Now we don't have a quantity that's meters squared per second squared, but we just saw one a minute ago. Remember this? Speed squared in meters squared per second squared. So perhaps this slope has something to do with the mass and the speed squared. We'll see that in just a few minutes. X variable here is not the radius. That's not the linear graph. It's 1 over the radius, or the inverse of the radius, if you will. Now, the y-intercept here is kind of bizarre, if you remember, with these inverse relationships, because there's no 0, 0 point here. Right? Instead, the y-intercept means that as the radius approaches infinity. This little arrow means approaches. So as the radius gets bigger and bigger and bigger, notice that the force gets closer and closer to zero. Inverse relationship, right? As the bottom of the fraction gets bigger and bigger, the fraction as a whole gets smaller and smaller. So as the radius approaches infinity, the force approaches zero. And it works the other way too. As the radius approaches zero, you would need the force to approach infinity. You need more and more force to make it go the same speed, but in a smaller radius. And in this third of the lab, where you varied the radius, you kept the mass and the speed constant. Mass at 10 kilograms, speed at 20 meters per second. So, we have now found three things, right? We know the force is proportional to mass, the force is proportional to speed squared, and the force is inversely proportional to the radius. And this is for an object moving in a circle at a constant speed. Remember that, right? That's what we're studying. And if you remember, when we have multivariables labs like this, when they're all proportional to the same thing, we can put them together with multiplication. So mass times speed squared times 1 over the radius, mv squared over r. A little combination that's going to be very useful in this unit. Right? This, again, allows you to change one thing at a time, but it also allows you to change everything. What if everything was doubled? What if we were looking at an object that had twice as much mass, twice as much speed, and twice as much radius? This gets a little complex, right? Twice as much speed would just be twice as much. Or sorry, twice as much mass would be twice as much force. But twice the speed, since it's squared, would be 4 times the force needed. So 2 times 4 is 8. And then twice the radius would be 1/2, because it's an inverse relationship. And 8 over 2 is 4. So if we doubled everything, we would need 4 times the force. That would really make a nice concept builder, right? So there's lots of variables we got to keep track of in this unit to see how that affects how much force we need to keep it move, a certain mass object move at a certain speed in a circle, constant speed, certain radius. Now, this is just a proportionality statement. It'd be much more powerful if we could turn it into an equation, and we can if we add in a constant of proportionality. I'm just calling this z. It's a dummy variable for now. Remember, this is some number that turns it from a proportionality into an equation. Sometimes we've had nice proportionalities. Newton's second law lab, we had a constant of proportionality that was 1 with no units. Beautiful. Sometimes they're more complex. We had very first lab of the year. The constant of proportionality between the circumference and the diameter was pi. No units, but, you know, not a nice number. You got to remember what it is. Sometimes we will see constants of proportionality that are both weird numbers and have units that you got to remember. It's just the way things work, right? But let's see what it is in this case. Okay, z is the constant of proportionality. So we have first third of the lab, second third of the lab, last third of the lab, and our general math model. Now the idea here, of course, is that if everything we've done is legitimate, all 4 of these equations should describe the motion. Right? All 4 of these equations should match reality. So let's kind of take them 2 at a time here, right, and compare them. We're going to compare one of our 3 parts of the lab to our general math model. So let's start with this one from our first third of the lab. First, I'm going to rewrite this equation. Everybody okay with that, right? They're all multiplication and division, so they're commutative and associative, so I can regroup them. Well, compare this equation to our specific math model we got in the first third of the lab. Look, we got the same y variable, the force. We've got the same x variable, the mass. We've got the same y-intercepts, 0. So if both of these equations are going to accurately describe reality, the slope that we found in the lab has to be theoretically equal to z, our constant, times the speed squared over the radius. This has got to be the slope. This is the y equals mx plus b, right, form of this. So again, compare these equations. This has got to be this. So then the question is, well, what does z have to be to make this predict 13.3 meters per second squared? Well, in this third of the lab, we kept the radius and the speed constant, so let's look at that. Speed squared over radius is 20 meters per second squared over 30 meters. Check out the units. This gets squared, so this would be a meter squared per second squared over a meter. Right? The meter on the bottom would cancel out with one of the squared meters on top, and leaving us with units of meters per second squared, just like our slope. And if you square 20, what's that, 400 over 30, you get 13.3. Huh. So the two things we kept constant, if we take the speed squared over the radius, we get a number and the units which are exactly the slope that we got out of the simulation. That's how they program the simulation, right? Which means, what does z have to be? What do you need to multiply 13.3 meters per second squared by to get 13.3 meters per second squared, right? It's 1. 1 with no units, because the units even, are the same. This is the best possible constant, because multiplying by 1 doesn't change anything, right? It's the multiplicative identity. So the first third of our lab is seeming to indicate that we can just plug a 1 in here for z and be done. But since we've got this other data, let's check it. Let's take this equation and make it look like the second part of the lab, second third of the lab. Y variable is force, x variable, speed squared, 0 y-intercepts. So this slope has to be z times the mass over the radius, right? This must be the slope of that linearized graph from where we got this equation. Well, in this part of the lab, we kept the mass and the radius constant. Notice, units check out. 10 over 30 is 1 over 3, which is 0.333 kilogram per meter. It's exactly the same as the slope. So once again, what do we need to multiply to make this number the slope? 1. So it looks like it confirms what we saw in the first third of the lab. Well, since we've got it, we might as well work through the last third as well. If I pull out the 1 over r over here to make it look like this equation, now the slope looks like it needs to be z times mass times speed squared. Well, we know the mass and the speed in this third of the lab. We kept them constant. Plug it in. 20 squared is 400. 400 times 10 is, of course, 4,000 kilogram meters squared per second squared when we square that out. Exactly the same units, exactly the same number. Z again has to be 1. So notice in all three parts here, it appears that our constant of proportionality is 1 with no units. And again, that's the world's best constant, because when you plug it in, there's no units to remember, and 1 doesn't change anything, so you don't even have to remember it's there. And so we get a math model that says that the relationship between the force, the mass, the speed, and the radius of an object moving in a circle at a constant speed is governed by the equation force is mass times speed squared over the radius. And again, this is for an object moving in a circle at a constant speed. Right? So a special relationship here. And again, only for things moving in circles at constant speeds, which, by the way, we'll give a special name to a little later on in the unit. So this was kind of our whole goal here, was that we have these, and now we can make predictions, right, of these things. If we plug in any 3, we can find a 4th, right? And we can solve for something else too. Right? If we plug in the force, the mass, and the radius, we certainly could figure out how fast it would be going, right? Any of these variables work with this equation. Now, here's an object moving in a circle at a constant speed, maybe like the bucket going around in a circle, right? We're going to call this motion uniform circular motion. UCM, sometimes abbreviated for. Right? Uniform, again, as we've used it before in here, means constant. So uniform circular motion is when an object moves in a circle at constant speed. Right? So you can say that, or you can just say UCM, or uniform circular motion. So we've got this equation now that relates force, mass, speed, and radius, right? Let's talk about one other quantity that often comes into play when we're talking about motion, right? And that is acceleration. Is this thing accelerating as it moves in a circle at a constant speed? Well, little clue here. First of all, let's think about, what does acceleration mean, right? Acceleration is not how fast you're going. It's how quickly you're changing your velocity, right? It's how quickly the velocity is changing. It's the slope of the velocity time graph, right, is the acceleration. So in other words, for something to accelerate, the velocity has to be changing, right? Objects going at constant velocity have zero acceleration. Right? So really, we can answer this question by deciding, is the velocity changing? Well, let's think about that for a second. Let's stop it right about here. It's going around clockwise. At this point, what direction is the ball moving? If I wanted to draw, I'm going to draw a velocity arrow on this dot right here, okay, at this point. Well, if you watched the IVV, you know what direction it would go. It would go off like this. Right? It would go off to the right in our picture. Now again, if you don't believe me, if you think it would go straight out or go in a curve or do something weird, watch the IVV because they do a wonderful little demo from above looking at something like this. It's really clear to see which direction it goes. Now note, if I drop a radius in here, right, from the center of the circle to the ball, there's an angle in here, right? It's a 90-degree angle. So this velocity actually has a special name. It's known as the tangential velocity. That's a fun word, tangential, right? The tangential velocity. It's the velocity an object has that is moving in a circle at a constant speed, right? Its velocity is tangent to the circle that it's moving. It's always at right angles, okay? Well, that's just at that point. What about other points? Okay, we'll watch this as I put it into motion. And so I left some behind at, kind of the 4 main points there, but you can see it as it goes around. Check out this velocity arrow. Is it exactly the same as this thing moves in a circle at a constant speed? Now you might be saying, well, it's always the same size because the speed is constant, but is there something changing about it? Look at that arrow, or look at these 4 arrows. Is this arrow exactly the same as that arrow? No. This one's pointing to the right. This one's pointing down, left, up, right? It's constantly changing direction. And velocity is a vector quantity. Right? Very careful up here to say it's moving at constant speed, right? Not constant velocity, because it is constantly changing direction. And if it's constantly changing direction, it's changing its velocity. And if it's changing its velocity, it's accelerating. And if it's accelerating, there has to be a force acting on it. How big of a force? We just figured that out, right? mv squared over r. Has to be the size of the force to make it accelerate so that it moves in a circle at a constant speed. See how all this goes together? One big logic puzzle. So again, it is accelerating because it's constantly changing direction. Right? We're not going to talk about things really speeding up and slowing down while moving in circles. That's kind of beyond this course. We do that in APC when we talk about rotating objects. Okay, but in here we tend to stick with this special case of moving in circles, but only at constant speeds. So that kind of begs the question, well, if we can calculate the force that we need to make this object move in a circle at a constant speed, uniform circular motion, can we calculate the acceleration it would have? Well, take our equation, right, that we just derived as part of our experiment. Right? Let me rewrite it a little bit. Again, I can do it. It's all multiplication and division. It's commutative and associative. And now let's compare this to an equation that tells us about force and acceleration. Of course, Newton's second law. Look, we've got net force here, mass here, and therefore the acceleration must be the speed squared over the radius. There's an experimental proof of the equation for an acceleration of an object moving in a circle at a constant speed. It's speed squared over the radius. Now, realize that this kind of makes this special, right? So we do have one special acceleration we know about already, which is free fall near the surface of the Earth, right? And we just know if we're dealing with a free fall problem or a projectile motion problem, it's just a given that the acceleration is negative 9.8 meters per second every second. Well, now we have a second special acceleration. If an object is moving in uniform circular motion, we can calculate this acceleration just by using this equation, speed squared times radius. Multiply by the mass, and that's the net force you need to get it to accelerate that way. So, again, I hope that you looked at the IVV because it would really help to see the demos, right? And we'll see other ones as we go throughout this unit. And then the next thing that the movie that you're supposed to watch is going to be a proof of all of this. And it is a gorgeous proof. Uses tons of physics and math in order to do things, right? In order to prove that these equations that we just derived for the force and the acceleration that we got experimentally, that we can derive these theoretically as well, which is always, of course, a nice, fun thing to do. So I hope you enjoyed this post lab for the Central Force Lab.